Okay, so right. So today I'd like to talk about the role of geometry in representation theory of p-adic groups and the relation of this picture to the Langlands program. So of course, I mean, I have 35 minutes, so this will be a very narrow slice of the picture, but I hope to, I'll try to highlight one story arc, and then if you would like to, yeah, please ask questions about relations to other things, and then and I'll either say something about it, or I'll say I don't know, and etc. Okay, so let me get started. So in the representation theory of p-adic groups, there's a class of objects that's sort of the core of, or in some sense, the smallest possible things, interesting class of things to study. And these are, people call these kind of the building blocks of the representation theory of p-adic groups. And that's because everything else can be built out of these. And this class of objects is called the supercuspidal objects. So these are the supercuspidal representations. And I'm sure over the next week, we'll hear a lot about supercuspidals from various perspectives. And so to justify this building blocks terminology or analogy, I'll just state a fact right here, which is that any smooth irreducible representation of a p-adic group can be realized as a sub-representation of parabolic induction from a supercuspidal. And so how one should think about this is parabolic induction is it's an easy process, and supercuspidals, this is a hard thing. And so what this is saying is that the smallest piece of non-trivial stuff inside this category of representations are exactly these supercuspidals. And so these are the things that we are going to study or to focus our attention on throughout this talk. And so let me give you do you see is my screen changing?
No, it's not.
I see. The first. I've already gone through multiple slides. So okay.
Oh, so, no, sorry.
Yeah. Okay. Let me try again. I'm not exactly sure what happened. Share. Okay.
Yes.
Okay.
No,
so
it is.
Okay. So this was I'll just quickly go through so you can see. So this was the first page. This is more or less, I just said everything that's on the slide. So this is our fact. Okay. And so let me begin now by giving you the simplest possible recipe for how to build a supercuspidal. So to give you a flavor of what these things feel like. And so this is the kind of prototypical recipe of a supercuspidal. And this is illustrated in the easiest case, which is the setting of depth 0 representations for SL2QP. Okay, and so the starting point is to take a representation, an irreducible representation of SL2FP. So this is just, it's a finite group, right? So, and once I have this, well, I'm trying to get to SL2QP, right? But one thing I do know is that I have a surjection from SL2ZP to SL2FP. And which means that any representation over here, I can pull back that action to an action of SL2ZP. And now I have in my hands a representation of SL2ZP. And then once I have that, I'm just going to take an induction all the way up to the big group. Okay, so it's compact induction, but and this is related to smoothness. But please just think of this mainly as induction. You're kind of averaging the action over a much bigger space, an infinite dimensional space. And the key here is that if I follow this recipe and I end up with an irreducible representation, then this representation is automatically supercuspidal. Okay. So let me say some things about, so this step is an easy step, as is this step, right? And so the main non-trivial stuff in this depth 0 case is coming from SL2FP. And a classical story from resolved maybe 40 years ago by Lustig is that the representation theory of groups like SL2FP, this is actually kind of a complicated thing. It's not easy to study these from a purely algebraic perspective. in order to get a full picture of what the character tables of these finite groups of Lie type, what these look like, one has to use algebraic geometry. And the way one uses algebraic geometry is one constructs some algebraic variety over FP or FP bar, and it has actions by appropriate things, and then these pi zeros will then come as kind of torus eigenspaces in the cohomology of this algebraic variety. Okay, so this is the basic recipe, and we're going to now talk about how to change parts of this recipe to get representations that aren't depth zero but deeper things. Okay, so higher depth, I mean, maybe it's better to just say deeper because, okay, deeper. Well, there's a couple approaches, one which is has more history to it, and one which has less history to it. And so the one way to make this this recipe 1, 2, 3 produce more interesting representations is to change 2. Instead of just pulling back along the surjection, maybe you supplement it by building up some other stuff. So you have some complicated recipe replacing this easy step in step 2. And this is the approach that has been taken since maybe the 1980s in constructing supercuspidals of arbitrary depth. So you keep step 1, you keep step 3, but you make step 2 super difficult in an algebraic way. And recently, in the last 20 years or so, another approach that we can take is a more geometric approach. Instead of changing 2 to be something difficult, we're going to change 1 to be something difficult. So we keep 2 to be this easy thing of pulling back, but instead of taking something like x0, we're going to build some other algebraic varieties that we'll call xr, and the cohomology of this in this SL2 setting will be a representation of not SL2 FP, but SL2 ZP mod some higher power of the uniformizer, some P to the R, let's do R plus 1. So I put R plus 1 because when R equals 0, we want ZP mod P, which is FP. Okay, and so the focus of today will be to talk about progress in this direction, in this geometric thing where we replace step 1 by some deeper representation coming from geometry. And I just realized I don't have the chat up. So yeah, so now the chat is next to me. So if you have any questions or anything, please feel free to unmute yourself or also type in the chat. Okay. Okay, so let me tell you about these varieties right here. Okay. So this is a joint work with Alexander Ivanov, and what we do is we establish this a construction of these XRs for arbitrary groups. And so the starting point is G, a connective reductive group over F. So for example, SL2, and then together with an embedding of an elliptic maximal torus. Whatever that means, this word elliptic means that associated to this choice of a torus inside my G, I can uniquely associate something called a Parahoric subgroup, which is for us will always be denoted by GX0. And this is kind of an integral version of a parabolic. So like an integral version of the integral version of a Borel subgroup, that's called a Iwahori. And that's an example of a Parahoric subgroup. And so in our SL2 situation, SL2ZP would be my Parahoric. But you can also do other things, you know, various congruent subgroups inside SL2 ZP. And this GX0, this Parahoric subgroup, crucially comes with a filtration of congruent subgroups. So I can change this 0 to an R and get some smaller subgroups. And in the SL2 situation, these are just congruent subgroups in the way that we're familiar with. So if my GX0 is equal to SL2 ZP or OF, then my GXR is going to be, all things inside SL2 ZP that are congruent to the identity modulo some sufficiently high power of the uniformizer. And so the advantage now is that when I take a quotient of GX0 by something like GXR, what I'll get is an SL2 of ZP mod some power of the uniformizer. Okay, and so this is where I'm going to see depth. Instead of just doing SL2 ZP mod P, I'm going to do SL2 ZP mod P squared and so forth. And that's the advantage of this setting here. And so on this next page, I will write down what the definition of this XR is. It's kind of technical, and I'll say what parts to focus on. Okay, so whatever this thing is, it's stuff inside a quotient of the Parahoric, such that X inverse times Frobenius of my point. So this is the Lang map right here. That's inside essentially the unipotent radical of a chosen Borel. So this is a unipotent radical of a chosen Borel B, which contains my original torus, which was called S. Okay. And the important thing about this is that it has two actions. It has an action by the Parahoric subgroup, and it also has an action by S0. And why is this good? This means that if I take the cohomology of this XR, in other words, I take this algebraic variety and I produce vector spaces, those vector spaces will also have actions by GX0 and also S0. In other words, from this variety, together with these two actions, I can build representations of the product group GX0 cross with the torus S. Okay. So this XR here, this is a generalization of a construction that Lustig did in 2005, 2006-ish, in the equi-characteristic setting. So in the case that instead of having QP, you have Laurent series over FP. And then Stasinski a few years later extended this construction to the mixed characteristic setting so that you're allowed to have QP. But both of these works were in essentially the hyperspecial case. And what I mean by that is this was in the setting where you had something like where this GX0 quotient by GXR plus was some reductive group evaluated at some finite ring, something like this. But if we're going to use this kind of construction to get at representations of p-adic groups, we really genuinely want to understand what these XRs are, not only for groups that look like this, but groups that don't come from a reductive group evaluated at a finite ring. So a larger class of Parahoric subgroups. And so this is what Ivanov and I did. And what we proved is that if I take a essentially sufficiently generic character of my S right here, and I consider the cohomology of this XR, and only the part where the torus acts by this theta, then I pull out a representation of GX0, and that representation I pull out is irreducible. Okay. And so what the purpose of this is that we want to, our goal, right, is to replace step 1 in our 3-step recipe from X0 to XR. And so what we need to know then is that after I do my 3-step recipe, I will actually end up with an irreducible representation and therefore a supercuspidal representation. So in words, what I mean is that given this theorem now that we know that this geometrically arising representation is irreducible, we have 3 gaping questions. The first big question is, when I take this representation and I induce it all the way up to the p-adic group, is that resulting thing irreducible? If it's irreducible, remember it's supercuspidal, so that's good. We're looking for supercuspidals. The second thing is there some other way to describe this representation? cohomology is somewhat mysterious. So maybe there's an algebraic way to describe it, or a kind of mix of algebra and geometry. So that's the second question. And the third question is, now that I have this this object, this representation coming from geometry, what is the role of having this description in the Langlands, within the framework of the Langlands program? And all three of these questions will be stated in Theorem 2. We're in joint work with Masao Oi, we're able to resolve all three of these questions simultaneously. And so so the rest of the talk will be focused on describing answering these three questions. And to begin with this, I will start talking about some Langlandsy things. So what I want to do is I want to construct some L packets. So L packets. Okay, maybe I stop briefly to see if anyone has any questions. Okay.
So in your theorem, you're not assuming X is hyperspecial. X is any.
No assumptions on X. Yeah.
Okay.
So it's any point in the building as long as it appears inside the apartment of a maximal unramified torus. So this is a very general class. So for instance, it includes Iwahori, it includes hyperspecial, and Iwahori hyperspecial are kind of diametrically opposite in the range, and everything in between as well. So it's yeah. So there are no assumptions on what I'm allowed to take my parahoric to be. Okay. So L packets. In the 1990s, Adler constructed a pretty wide class of supercuspitals using a construction that was later generalized by Yu to give us what we now know as the most general construction of supercuspital representations. And these assumptions that I had on the theorem, this toral in general position, depth R is them, but these two conditions, these were exactly the same conditions that Adler had on his starting point. And what Adler's construction went like this. He said, you give me an elliptic torus inside a group G, together with a character theta that's sufficiently generic. So sufficiently generic means you want it to be very far away from the trivial representation. And then from this theta, I will produce for you a supercuspital of G. And that supercuspital of G, for this talk, we're going to notate it by pi sub t theta, and then with this alg. So we know this is an algebraic construction of a supercuspital coming from this data t comma theta. Okay. And so once we have a construction like this, then it's natural to ask how these supercuspitals come together in L packets. Okay, so how do these come together in L packets? Well, what are L packets first? L packets are finite collections of supercuspitals that should satisfy many very nice relations. For instance, there should be some kind of good relation. I mean, the formal degree of the representations inside your packet should be constant. There should be something called stability. It should satisfy endoscopy, character relations, all these kinds of things. And the property that I'd like to focus on is a notion of stability. And the way to think about stability, coarsely, but this is captures in some sense the essence, is it's some kind of constancy under conjugacy over the algebraic closure. So this is G of F bar, not just G of F, not just rational conjugacy, but conjugacy over the algebraic closure. Okay. And so what's the point here? Well, the thing is that this left-hand side, there's a notion of there's a notion of stability on this side, and there's also a notion of stability on this side. And so one natural question you could ask is whether or not this recipe preserves that stability. And this was a conjecture of Reeder in the 2000s. And what he said was, okay, well, given Adler's construction, I'm going to form an L packet by taking all the supercuspidals that are associated to a stable conjugacy classes of these t comma thetas, right? So in other words, this conjecture says that stability should be preserved under Adler's recipe. And what Reader proved is that at least this finite set of supercuspidals satisfies the constancy of formal degree property, which is just if you look at the formal degree of every member of this packet, it has the same as all the other things inside the same packet. Okay, so we have constancy there, but he did not prove stability. And then some years later, the plot twist here is that in fact, this recipe does not preserve stability. And this was proved by de Backer and Spice maybe around 10 years later. And the thing here is that, so this recipe does not prove stability. In order to get the recipe that does prove stability, you have to make a twist before you take this recipe alg. So you take first take a twist by some character that depends on this input data of t and theta, and then you apply alg, and then you get a representation, and that is the correct normalization. So the takeaway here is that this alg is not the right map. It's not the one that preserves stability. So it's not the one that's well compatible with Langlands. Okay, and so let me write down the recipe based on this slide that does. So the recipe then, is that I take my t theta, that was my starting data before. My ending data before was just this pi alg, right? And what we're going to do is to insert this twist by this character right here. And remarkably, this character is a quadratic character. This character only takes values in plus or minus 1. But that plus and minus 1 is enough to mess up all the stability. And so once we put this correction term here, then this resulting composition will preserve stability. So that's the theorem of de Backer and Spice. Okay, but now, so what does this have to do with the geometric stuff that I was talking about before? How does XR come into this picture? Well, remember XR before came to us from exactly this data. I take a maximal torus together with the character of that maximal torus, sufficiently regular, satisfying these same conditions over here. And then I can produce a representation of G from taking the cohomology of my XR. And so remember, we had these 3 questions. Is this representation supercuspidal? What is this representation, and how is it compatible with the Langlands correspondence or conjectures? And the answer to all these 3 is exactly this equality right here. And so this is theorem 2. Theorem 2 is that when you take this representation that comes from the cohomology of XR, it in fact is on the nose equal to this twisted construction on the algebraic side. Okay, so this geometric thing is this twisted algebraic one. This twisted algebraic one was the one that's twisted to be the correct one with respect to building L packets. And so I just write a summary of what I said here, which is that theorem 2 answers these 3 gaping questions that we had before. Once we developed this XR, we wanted to know the answer to these 3 questions, and the answers are: it is irreducible supercuspidal. It is equal to this representation that has a totally different construction, and also it gives a geometric realization of these L packets. In other words, this natural correspondence coming from XR is on the nose the one that preserves stability. Okay. And so let me, I'll pause again here before telling you some the key that important feature in proving this theorem. Okay. So the key insight in proving this theorem, let me rewind. So at face value, what are we trying to do? We're trying to say that this representation that comes from geometry oh, oops. This representation that comes from, this representation that comes from geometry is isomorphic to this representation that comes from algebra. And in representation theory, what you learn in your first class in representation theory is that one way to prove that two representations are isomorphic is to prove that their characters are the same at every single element, right? Just taking the trace of all the images is enough to remember the representation. Okay, so that's one thing we could do. We could say, okay, well, if I want to prove that this is isomorphic to this, I can just calculate the character on both sides and show that it's equal. But the issue with this is that this is the characters of these are very complicated. And moreover, when you calculate the character of some representation, that calculation is intrinsic in terms of how that representation was constructed. In other words, the character formula that you get from an algebraic construction will look drastically different from a character that you get from geometry, because the origin of that construction is so vastly different. Okay. So what can we do instead then? The key idea in proving theorem 2 is that sometimes you're in a situation when a representation can be recognized from the character at only a few of the elements. So there's some special elements where the character behaves very nicely, has a very simple formula. And on those characters, it's actually enough to determine the entire representation. And so that's this sentence here. The key insight in proving theorem 2 is that one can recognize certain irreducible representations by their character on a particular locus of elements, which are called very regular elements. This terminology, very regular elements, is terminology of NER, and I'll say what that is in an example in 1 minute. Okay, so this is the key insight, that you don't need the entire character to characterize a representation. Sometimes you only need a small locus. And this is not in itself a new idea. This is something that has a rich history of situations where this has been very useful. And so I mean, the oldest actually, so the oldest is in the representation theory of real groups. This is a celebrated theorem of Harishchandra, where he said that the discrete series representations can be recognized by just looking at the character on regular elements of compact maximal tori. And this result was very important because this is what this is what Langlands used to do the Langlands program for real groups. And in the p-adic direction, when your group is GLN, this is a theorem of NER, and that's where the terminology comes from. So very regular, as I mentioned in the real group setting, very regular means just regular elements of a compact maximal torus. And very regular in the p-adic setting in GLN means the following. So I'm going to write down the example just for GL2QP. So inside GL2QP, there's a subgroup given by L cross, where L is the degree 2 unramified extension of QP. And this is alpha inside L cross is very regular if this alpha first is inside the units, and moreover, its image inside the residue field doesn't sit inside any smaller subfield. So it's in FP star just by assumption, but it's not in FP. It's in FP squared star, but it's not in FP star. So if it was in right. So it's like, so the kind of theme of this is we want things to be away from the center. We want things to be away from the trivial character and so forth. So very regular is this kind of notion. Okay. And so this was, actually, I don't know when this was proved. This was proved in the 1990s. And what Oy and I did in this project is to establish the analog of this for p-adic G, for arbitrary G. And this fills in a piece in Kalitha's construction of the local Langlands correspondence, in that one can now do what Langlands did for real groups using Harish-Chandra's characterization. Okay, so again, we have this stuff, and then we should ask, how is this related to XR? How is this related to the cohomology of XR? What does it give us there? And unfortunately, none of these 3 bullet points actually help us figure out what the compact induction of the cohomology of XR looks like. And the reason is that we don't know, so these don't apply yet to the compact induction of this cohomology. These don't apply to this. And the reason is that we don't know if this representation is irreducible. And if we don't know if it's irreducible, then we can't use the characterization of irreducibles on it. And so what we do is actually prove something like these, prove a Harish-Chandra-esque characterization, but not at the level of G, but at the level of GX0, at the level of this smaller, this representation here, where we do know irreducibility. So I just wrote this here. To prove theorem 2, we need to have this kind of characterization for Parahoric subgroups. And this turns out to be much more involved than, for instance, these two. And the reason for that is that the representation theory of Parahoric subgroups is in fact much more much more badly behaved than for p-adic groups. And there are various results that tell us that the representation theory here is much harder. And so accordingly, it's much harder to prove this kind of characterization theorem for Parahoric subgroups, and it involves several tricks that we basically luck out on, like threading the needle in some sense, plus a good analysis of what Adler's construction is, so the algebraic side. Okay, so I'll wrap up in the next minute here. And what I'd like to do now is to just give a summary of the ideas that have gone on so far in this talk. And so the takeaway. So what is the takeaway? The takeaway is that if you want to give a geometric construction of these supercuspidals, but you don't only want depth 0 supercuspidals, you want deep supercuspidals, then what you can do is to define these XRs for arbitrarily large R, so that gives you arbitrarily deep supercuspidals. And these are analogs of Deligne-Lustig varieties for in the depth 0 situation. From this, you can consider the cohomology and compactly induce all the way up to your p-adic group. And the theorem there, the assertion there, is that when you do this, you get an irreducible supercuspidal representation. Moreover, this recipe that has fallen into your lap because of this variety XR from these pairs to these supercuspidals, this preserves stability. It's compatible with Langlands. These were proved by establishing a Harish-Chandra-esque characterization for representations of GX0. And the important thing here is that for whatever reason, even though our algebraic construction missed the mark by this extra twisting, by this Zide, this Debacker-Spice twist of plus minus ones, this XR knew about L packets. It already knew, it was inherent to XR that it should behave well with respect to the properties that we want L packets to have. And so now that we have these theorems, the natural question to ask is there a geometric explanation for all of these? Why is it that XR intrinsically knows about the Langlands correspondence? And so I will stop here. Thank you very much.
George? Questions or comments?
I have a question. So, does everyone hear me?
Yes, yes.
Yeah, okay. So this XR variety, do you have like some easy example of how to realize this? Like, is it like a homogeneous space or some, like the whole group divided by this paraholic or something like this?
Yeah, so the here's one I think this is a not so bad way of, okay, so here's the definition is you take these quotients and inside this you look at the part that comes from a unipotent radical of a Borel. There's a map from this quotient to itself, this to itself, given by the Lang map, which takes G to G inverse f of G. And so you know the kernel of this map is the rational points. And so this XR is it fills in this square.
See.
Oops, this is the other arrow. Yeah, but right. So let me give you maybe an example. So when R is equal to 0 and we have SL2, this X0 is called the Drenfeld curve, and it's just the vanishing of xy to the q minus xqy equals to 1. So it's the a curve defined by this.
Mm-hmm.
When so how do we get XR from this? Well, this is simply xy such that the determinant of xy x to the q, y to the q is equal to 1. And so what we'll do for XR is take this same equation, xy, but now instead of just taking things inside here, this two-dimensional affine space over FQ bar, I'm going to take it over the Witt vectors of some truncated Witt ring. And then take the same thing, determinant of xy, sigma of x Frobenius of x Frobenius of y is equal to 1. And that is the XR in this special case of SL2.
Okay, thank you.
And yeah, so and we also know other things like that these XRs behave well with respect to affine Deligne-Lustig varieties in special cases, and so they really do appear in various incarnations of Fly varieties. Yeah, thanks for your question.
Thank you.
I just looked up your paper and I noticed that you have a condition that Q has to be large. And I'm wondering how serious this is, because I'm in the market for results of this kind for a small application, but with Q equals 2 and 3. So that's
yes. So the reason we need so this is something that of course I hid under the rug, and if I had 20 more minutes then I would say more about this. So thank you for the opportunity to talk about this subtlety. We have this condition on Q equals large and or Q sufficiently large, and the condition that we need here is that if you take an unramified torus and you look at the regular elements inside this, we need this to generate the whole torus. And so so this is this is the precise thing that we need for Q equals a Q large. And this is it's not very serious at all. So but the only way we know how to prove this as right now is to actually give a list of, Carter has these calculations of what the orders of various maximal tori in the reductive groups over finite field setting, and we use those to write down exactly which Q are excluded. And so I think, oh man, I forget. Well, the Q that we have to exclude are less than the Q that have to be excluded in use construction, which means that it might be that in your situation, P equals 2 may still be omitted. So for instance, P equals 2 is always omitted in in use construction because of the appearance of the Bay representation. And P equals 3 is not always excluded. So, so here's an example of one situation where our theorem does not work. So theorem does not work for SL2 and P equals to 2. And the reason it doesn't work here is that use construction isn't there. But the interesting thing here is that the XR exists regardless of what your prime is. The XR doesn't care about small characteristic. And so even though use construction isn't there, this representation XR, or this representation is still there, and one can still ask what this compact induction is. And in this case, yeah, I think this is an interesting question. I think this breaks down into two new supercuspidals that actually don't appear in use construction in the P equals 2 case.
I'll address this in my talk next week.
I'm looking forward to it. Yeah.
All right. Any other questions, comments? All right, let's thank the speaker again.
Thank you very much.